working.
Find the red button on there, Ralph?
Yeah.
Is it recording or just taking snapshots?
It's just working. I think so.
Good morning, everybody. This is Raul Duda taking a video, so you can deal with him. Yeah, there he is. He's waiting for you. Okay, so on Wednesday, we were talking about reduction potentials and oxidation potentials. Did I show you that table in the book?
Yeah.
Okay. Did we talk about how that is only for reductions? What do we do for oxidations? We go to another table? Use the same thing, just for each reduction that's on there, those can all be turned around to become an oxidation. Because for all these in the book, electrons are on the left side as reactants being gained. So gaining electrons is always reduction. Let's just take a look at whatever it shows up at. Some of these on the bottom of the first column. I'll even zoom in some. All right, notice that all these half reactions, electrons are being gained. Electrons are on the left side for all of these. If you need oxidation, just take these and turn them around. And whatever the products of these reductions are, those would be the reactants for oxidation. Now when you do that, you're going to take the reduction potential, which is over here, and change the sign. These are all positive reductions. So when the product is being oxidized, turn around. Those would be negative oxidation. We'll use this table a lot. I will make a photocopy for you just to have easily accessible. Because you're going to have it, you're going to be turning there all the time.
Beginning of my
Okay.
Hollywood journey.
All right, so this is where we'll begin today. What would be the cell potential for this? And you don't have to grab a book. I'll just go through the numbers with you. Is this a redox reaction?
Yes.
How do you know?
Because the fused charge that change and the
Charges
Fe
are changing.
Yes.
Yep. The iron is being oxidized and the copper is being reduced. So what we would have to do to find the cell potential, that's what this thing means. E cell is cell potential. We're going to find the reduction of copper to iron and the oxidation of iron to iron 2 on the table. So let's see, I'm going to have you write these down because I'll have to scroll off of it. Up here, the second one from the top, in the second column, is the copper reduction. I'll have to zoom out just a little bit, see if I can get the reduction potential in there too. There it is. Okay, good. So the reduction of copper 2 to copper metallic is 0.34. Write that down for yourself. Reduction of copper 2 is 0.34 volts. That's volts. That means copper is good at accepting electrons. Copper ions are good at accepting electrons. Now, for the oxidation of iron to iron 2, what we're going to do, and at first you don't know, you just have to look through the whole table, but oh, I see that right there. There's a reduction of iron 2 down to metallic iron. We actually need the oxidation of metallic iron to iron 2. So we take this reaction and we turn it around. Just go the other direction with it. Now, that would be the oxidation of iron to iron 2. And so the oxidation potential, you would change the sign on this one, become positive 0.44. Are you with me? Okay. So for the oxidation, you do have to train your brain to deal with this because you'll be looking for the oxidation of the product. You're not looking for the oxidation of these things that are in the reactants. Those are for those reducing. You have to look at the products and turn them around so that they sorry. Okay. So here's our numbers that we came up with. The reduction of copper, I left the electrons out of it because they're balanced here. The reduction of copper has a reduction potential of 0.34. The oxidation of iron has an oxidation potential of 0.44. So for the overall cell potential, you just add together the reduction and the oxidation. And this would give 0.78, positive 0.78. Can you imagine that there would be cells that we would put together that have a negative reduction potential? Not reduction, negative cell potential? Do you think that could happen?
No.
What if we have iron positive 2 and copper neutral? It would be negative there.
Yeah.
So it is possible. Here's the part that I want to mention, right here. You'll know a redox reaction is spontaneous only if its cell potential is positive. That's how we know if a redox reaction is going to be spontaneous. Yes?
But like if something's not spontaneous, it can never occur, right?
It can occur if you do work to it.
If you do work to it, you're changing the environment and hence making it not spontaneous.
Yeah. No, it's already not spontaneous.
But then like when you're
Causing
applying,
it to happen.
Yeah.
But that doesn't make it spontaneous. It happens because you're putting work into it. Like if we turn this reaction on, if we have metallic copper, like a penny, and we put it into an iron solution, iron plus 2, that penny will stay there all day, nothing's going to happen.
Yeah.
But if we take a nail, which is made of copper, I'm pointing at iron, it's made of iron, nail is made of iron, and we put it in a solution of copper, that will react. And the copper is going to reduce on the nail is going to dissolve, and it's going to make those products. And that happens spontaneously, that will happen. Now you can get the opposite reaction to occur, you just need to do something, and we'll see what that something is. A little fun there next door. That something is you'd have to use a power supply to push the electrons in a way that they wouldn't naturally go. And that can be done.
Every now and then we should scream a bit louder to make it
To
seem
make
like,
them
yeah.
feel bad, like, oh, they're having fun next door,
Yeah.
and we're not. Okay, now with regard to that table over there, on the previous slide, I really should have had that degree sign. I didn't, but they should have been there. Like these should all have a degree sign. This chapter is going to be very important to know when we use that degree sign and when we don't. Now, the degree sign is not really degrees. It represents the term naught, N-A-U-G-H-T, naught. We'd say epsilon naught for that term. That represents standard conditions. Standard conditions specifically are 1 mole per liter solutions for all of our aqueous things and 1 atmosphere for all of our gases. And that table that we use in the back of the book is only good in standard conditions. That represents the standard reduction potential.
Good one, Mr. Moore. This is so fun.
Wait, so standard reduction was like
See, they quieted down already.
the STP, this is the SRP,
It's like STP, yeah. Yeah. It's not the same conditions. Because STP for gases is 0 degrees and standard conditions is 25 degrees for thermodynamics and reductions. What's that, Patrick?
Hilarious, Patrick.
It's pretty good. How challenging is electrochem? It's not that difficult.
Oh, it's not difficult. Oh, yeah.
Dude, what happened to the chemistry joke of the week?
George gave up because people were defiling it. Well, before you sit down, Tish, would you close the door for me? So we don't get too jealous of them.
Is he still gonna come in every morning? Then we can write a note to him like, "You want it back?"
You can't. Everybody else will read them up.
Right.
Now, this last bullet point is going to be troublesome because you're used to, if you change an equation at all, then whatever goes with it, like the delta H or the K, equilibrium K, then you change those too in different ways. But when you have a reduction or an oxidation potential, if you have to multiply the equation through by something, you don't change the reduction potential or the oxidation. You're going to have to get used to that and tell your brain not to do that because it wants to. So we'll go over examples of this. I'm just throwing this out right now. But just be aware that these half reactions with their potentials are just treated a little bit differently than what we've done in the past.
Good job, Jinsu.
So if I have a cell with a salt bridge, a cell always has a metal bar in each compartment, and the metal bars have to be connected by a wire. Those metal bars are called electrodes. Like in my potato clock over there, I've got one is zinc and the other one is copper. And the zinc is sending electrons over into the copper. So anyway, maybe I'll use zinc and copper. If I want to know what the potential of that cell is, if I use the table, then I need to assume that I have 1 molar of zinc ions in this container and 1 molar of copper ions in this container. If I don't have 1 molar, then I will not correctly predict what the voltage of that cell is. That table only applies to standard conditions. Now, is it possible to figure out what the voltage would be if I'm not in standard condition? Yeah. You have to calculate a little bit more, and we'll see how to do that. We good with that?
Can you explain why the electrode doesn't have a charge? Like, in the, for the reading quiz, like why it wasn't PV plus 2?
Yeah.
In the reading quiz, the question was, what is oxidizing? Or, yeah, what's oxidizing,
Yeah.
I think, right? In this case, the electrons are flowing this way, so the zinc is what's oxidizing. You can't have Zn positive 2 oxidized because zinc doesn't go to a higher oxidation state.
Oh.
It's only the zinc neutral oxidizing, gives off 2 electrons and becomes zinc positive 2. So throughout this reaction, as the reaction is going on, the zinc bar is dissolving. It's the bar that's the oxidizing thing,
Okay.
not the zinc ion. I didn't mark it wrong if you put Pb
Yeah.
plus 2, but it was wrong.
Okay.
Over here, the copper 2, this thing right here is reducing. It's not this that's reducing, it's this thing right here. Because the electrons are coming in, and the copper ions are accepting the electrons. And yeah, this is going to get smaller, this is going to get bigger. Yep.
You said there's no charge going through the salt bridge. Why?
Not that there's no charge, there's no electron flow through the salt bridge.
So
The salt bridge is full of positive and negative ions, and as the zinc oxidizes, we get more and more positive ions in here. Negative ions have to come in from the salt bridge to keep the whole thing neutral.
Yeah.
The whole thing meaning this beaker has to stay neutral. You can't build up positive charge.
Yeah. Also, nothing actually flows.
What do you mean flows? Yes, negative is flowing. Negative ions are flowing in.
Okay.
And positive ions are flowing in here.
So won't the tube like start to empty out?
Yeah, eventually your salt bridge is going to go neutral. Yep. I don't know. It's possible, I guess, that some of the negatives can flow out of here into there, and some of the positives can go out of there. I don't know if that happens, or if once the salt bridge just goes
So
neutral.
like,
it stops.
okay, so like the zinc place, the negative ion would come out, but then what would stop the positive ions from coming out with it?
Because if the positive ions came out, then it would build up positive charge in here. The negative ions are just coming in here to keep it neutral.
So after some time, we'll see like a bunch of like one ion on one side and one ion on the other side inside the salt bridge.
Yeah, like let's say the salt bridge had sodium chloride in it.
Yeah.
So the chloride ions are going to come into here, and so you're going to have zinc with chloride ions, and the sodium ions are going to go into there. So you're going to have sodium ions and whatever. See, remember, the positive 2 copper is no longer positive 2. It is grabbed onto the bar. It is reduced. But the copper had to start with maybe copper sulfate or copper chloride or whatever. So as the sodium ions come in here, you're going to have a solution of sodium ions and whatever the counter ions were for the copper. Salt. So yeah, the salt bridge is not really doing anything except keeping the charge neutral with both. Now this part is